Um, this is the interview for of Ted Roberts over the uncharted territory of quantum mechanics, quantum space theory. So we have Ted Roberts with us. He is theoretical physics, philosopher of physics, as of all theoretical physics are. He is the inspiration behind the New York Times best-selling book, Sex on the Moon, the amazing story behind the most audacious heist in the history. And frankly, if a movie will be made on this heist, I think that will beat Italian Job or like that, movies like that. And um, Alex enjoys actually he have been a astrophysics as an intern, and then sorry for the okay. So Ted at 22 was hired as on co-op at NASA's Johnson Center in Houston, Texas. He worked as an astrophysics, then geophysics, and eventually became a flight lead in Neutral Points Laboratory. And after some series of events, he found himself in theoretical physics and founded the institution, Einstein's Institution, which you may have the link in the description. You can check it up. And furthermore, he is the author of Quantum Space Theory, and we will have like him all over this interview. So we will start here, Ted. That was like very burst introduction, I think.
Thank you.
All right. Thank you. So, all right. So we are before we dive into like QST. Let us give our viewers a brief introduction about you. So starting with your early life, you were astrophysics and geoastrophysics and then the lead physics at the NASA. What was the experience?
Ask me more specifically, like what was it like at first or what was it like near the end?
At the NASA, people like me or the astronauts, they are inspired to be in the like NASA and stuff. So what was the experience? How you inspired to be in the astrophysics department?
So the environment there at NASA is something worth really talking about. It's a entire community of people who agree on, one of the major functions that we do in our existence is use the scientific method to explore more and ask more questions and get more answers. So everybody there was very on board with trying to learn and enjoying being associated with other experts in different fields right next to them, right? And not all places appreciate that, but that was a place that really, I found general appreciation of that, and people really leveraged it well. So that was great.
Like it was like kind of adventure there, right? So in like training the astronauts and their EVs and stuff like that. That's really kind of stuff like. So how did you actually shift it from astrophysics to the theoretical physics?
I don't know that I ever shifted. I just added. Right? I never really get rid of questions unless they're completely satisfied. But if you completely satisfy a deep question you have, you never move beyond that information. You always carry that with you because you genuinely understand it. So my search has always been to try to ask more questions that require me to add more fields instead of switch fields.
Okay, that's why. There's a question in my mind from after reading the next Sex on the Moon and your recent book, The Perfect Universe. That how actually what was the all the planning of that the moon rocks thing, stuff like that. Just an overview, just to inspire the people.
Oh, tell the general story.
Yeah, general story.
Oh my God, it's so long ago now. It's so funny that it still actually happened. We had this crazy idea to steal some moon rocks and sell them for a lot of money so that we could go fund some of our other scientific ventures without having to worry about getting grants or funding or being slowed down by the process that currently exists. And also the process that's really weeds out people asking the most fundamental questions, right? It makes it really hard to make a living asking the most important questions these days because of the ways money comes to people now, or the way you have to go about it. So we thought we were going to cheat the system and get a whole bunch of money right up front and fund fantastic research and change the world. And we were completely in love and also completely insane in a way, because we were just ignorant of how the rest of the world was going to take that.
All right. So actually, for our viewers, do not actually to follow that heist to just fund the things up, because I think terror because that is a, I think, discouragement in the scientific community, that when you ask the fundamental question, you cannot be funded until or unless you're associated with a very high profile and organization like CERN, NASA, and like.
Well, that, and also the way that academia is set up is that you basically have a grandfather and a father and a son. Right? You have advisors that teach you in a tradition and teach you also how to get funding in that tradition and how to make it so that people who have the money want to give further research money, right? So basically you get ruts where people have figured out how to get research money for very specific things, but it's really hard to get out of that now that the competition's tight, right? You have to use a different method, you have to go about different ways, and just there aren't really well-carved ways for individuals to take on individual paths, which is what we are supposed to be encouraging in science. We want to maximize the number of individual concepts and questions and queries that people are taking, and hypotheses, so that we can get maximum number of insights, right? 99% of all the things we can hypothesize are always going to be wrong, but we need to be encouraging people to hypothesize more, not less. And I find that the academia system right now is fantastic in many ways, but in one way it seriously could improve is to really try to focus on the emotional constraint that they've put right now, probably not intentionally, but they've emotionally constrained it so that people don't feel encouraged to hypothesize. In fact, they feel like, well, if I propose something, what if this, and follow it to its conclusion and find out that there's a contradiction, then I'm dumb because I assumed this from the beginning. And that's exactly backwards. What we should be doing is encouraging people to try some new thought and to find out how to prove it's right or wrong, right? To follow its consequences. Instead of punishing them or making them feel like it was a waste of time when they find out that that presumption was wrong, we should reward them for figuring out how to determine whether or not it was wrong. Yeah. Uh-oh, I can't hear you.
Sorry, pardon me. The mic
Oh,
was.
now I can hear you.
So on that note of the new idea, before diving into the QST, quantum space theory, I think we should set up a stage of like early stage of like de Broglie's interpretation, Bohmian mechanics, Bell's theorem of non-locality. Could you give us a brief introduction about it, because most of our audience or viewers don't have actually the knowledge of, like they don't know about anything other than a Copenhagen interpretation of quantum mechanics.
How familiar would you say the audience is with the Copenhagen interpretation? What do they know about it?
They're like simple undergrad course. You can simply there. They're like in an
Okay. Well, okay. We should start trying to be very, very specific, because when you explore quantum mechanics, you're exploring the edge of ideas, and really what you're exploring is the ways that the smartest people so far have come up with putting these patterns together to make sense of them. There's several interpretations of quantum mechanics, and the Copenhagen interpretation technically isn't an interpretation. It's a non-interpretation. It's the one that attempts to forbid you by definition to be able to interpret it, which is kind of insane. And in my view, it's almost anti-scientific, but it's still been the standard view for a long time in that specific part of physics, right? So it's not really an attack on physics, it's kind of but it is an attack on, we've become so wedged in specific things, people don't know how to challenge the basic things anymore. And people are now challenging. There's several brilliant people out there that are trying to point this out, not just me saying this, but technically we've bought into a model that says at the beginning, the foundations of this system cannot be understood, right? There is no logical system that writes this together deterministically. There is no determinism. That's built into the assumptions of the Copenhagen interpretation, which has been falsified. So basically, what I'm saying is, and Tim Moudon makes a fantastic post of this. So he explains it way better, but I'll give my best introductory shot here. The Copenhagen interpretation makes the assumption that you cannot deterministically model the effects of quantum mechanics. So all the actions, all the things we observe of the small world, when you measure something, its spin, or all these different properties of the small particles, Now, let's do even more general. The properties you don't need to know what necessarily are in order to talk about how they interact, okay? The truth is, nobody alive confidently knows what these properties are. Spin, charge, mass, color, right? Nobody knows what those things actually are. What we know is what they do, how they act on each other, how they act on the world, and so on. So there's certain relationships built into these quantum objects, these fundamental ingredients of nature, from which all of matter is built, that determines how they can have all these actions, all these bonds that they can form. It determines all the things that they can and cannot do, okay? The Copenhagen interpretation makes the claim that that cannot be deterministically modeled, those actions, that it's impossible to do. And the pilot wave theory has done it since 1952. So since 1952, nobody should have been in the Copenhagen interpretation, but it was so snowballed politically that it's been taught as the only version of quantum mechanics from the beginning, right? So, I mean, when I got my physics degree, we had one semester on quantum mechanics, and they never mentioned interpretations. They taught it as if there was one thing, and they taught the Copenhagen version. And I went away from it very confused, trying to figure out what is the probability amplitude? I don't get what it really means. And there's so many concepts in there that aren't explicitly clear. And it's actually because it's built into their assumptions. They literally built in that it cannot be made clear. And then they make the bold claim without any justification that you can never get past it. That restriction they put on an understanding is just a law of nature, even though they just made it up. So Bohm mechanics has completely broken that claim. It's shown that the Copenhagen way to go is definitely wrong. It doesn't mean that the Bohm mechanics one is right. You never know that you're right with a theory. You can just falsify them as you go, right? Excuse me. Okay, so you want to pitch in with a question, maybe see where I go from here?
Yeah, I guess we should dive into very briefly the QST, the basic idea of the QST.
Oh, okay. So quantum space theory, I'm not even sure if we're what we're really calling it. That's what I called it at the beginning when I was exploring an idea that kind of reaches back to carries overs of the original physics concepts that maybe Lord Kelvin had. And the idea is basically this, that the medium that all these interactions are happening in is a physical medium with very specific characteristics. It's not much of a bold claim, right? Because you could say, if we're talking about water, then water is, by definition, a medium of, and then you can list off all the properties that water has, right? And it has a lot of actual properties. It has index of refraction, it absorbs certain wavelengths of light better than others. And there's lots of things you can mention about water as a medium. It also has properties that characterize when it will undergo a phase change. So the medium itself can take on a different arrangement and a different meaning, right? So these are concepts we're all actually pretty familiar with when we just think about water. But when we think about space or space-time itself, the medium of physical reality in which all this stuff is supposed to be playing out, we've been basically, I was, and almost everybody I know was taught to believe that there is no ether, there is no medium, there is no anything. It's an absence of, right? Now, modern physicists no longer believe that, of course. Ever since Einstein, we no longer believe that we now call space-time is nothingness. We don't believe it's an absence of everything, because we believe it has particles. It has characteristics inside where particles are coming into existence and annihilating each other over and over and over on the small scales. All right, so my concept was to say, hey, let's just start from a description of the medium itself and characterize all of it, the medium's properties, but let's pick a medium that's as simple as possible. So the medium I picked was just a quantum fluid. And a quantum fluid is just a fluid, kind of like the way you think of water as being a fluid, but it's made of spheres instead of molecules. Molecules are made of 3 parts, right? Put just spheres at the bottom, and spheres that are undulating all identically. They can be out of phase from each other, but their max to min is the same, okay? So they have a frequency of the fundamental constituents of the fluid have a natural frequency, so therefore a cutoff in period. They have a minimum amount of time that can be measured in any action within the fluid. okay? But there's also a minimum cutoff of distance, the radius of the minimum piece, okay? So there's a minimum scale of length and a minimum scale of time in the fluid, and I haven't even mentioned how big the spheres are, right? I mean, it's just a general claim. So there's, if we have a fluid that's made up of quantized spheres that undulate, then there is a minimum cutoff of time and a minimum cutoff of space in that fluid. It doesn't mean if you get outside of the fluid, then you don't have a cutoff anymore. But within the fluid, there's a cutoff. All right, are there any other boundaries that exist by consequence of that you cannot escape? And it turns out there are. If you imagine zooming out, so you have all these spheres, right? If you zoom out until they become points, and all tiny, tiny points filling in, at some point, when you keep zooming out, you can no longer resolve, that you'll reach a scale in which you can no longer resolve that the fluid is made up of parts. From then on, no matter how many times you zoom out, the fluid, as far as you're concerned, only has characteristics that are befitting of a continuum, right? So there's another boundary. So we have two boundaries at the bottom. We just found another third boundary. There's another boundary between those two, and it's a scale boundary. You zoom in, so now that you can resolve the parts again, but at some boundary, some scale, if you zoomed in beyond it, you wouldn't be able to distinguish a boundary. You wouldn't be able to say, hey, this region is less dense, safely and continuously than this region. So you lose the ability to define a boundary on a certain scale. So at the scale in which you can have a stable boundary, if there was something happening, right, then that's an important scale too. The only other boundary left is the one that is the entire collection of the fluid. So the entire radius of however big the entire collection is. Since we're talking about this fluid being the substrate of our reality, then we're now talking about the radius of the universe being that last boundary. Okay, follow me so far?
Yeah.
Okay, so we're saying if we start with a general quantum fluid, as general as can be, because I haven't even given you numbers for these. We just said if it's made up of spheres, then we have that construction leads to 5 scale boundaries. One of them's time, and 4 of them are just radiuses of different sizes, right?
Yeah.
Different scales. All right. Well, it turns out that if you take those 5 scales and match them numerically with the 5 Planck constants, the Planck time, the Planck length, the Planck charge, the Planck mass, and the Planck temperature, those numbers, and treat those last 4 as all references to length, okay? Those numbers, those intersections, automatically determine how you carve up the fluid, right? If you put those Planck numbers in those intersections and then divide them all, you can take the first scale boundary divided by the second, or the third one divided by the first and second, or all those combinations, all those simple combinations with no scale factor, with no 4.372 out in front of it, just ones, okay? Then all those simple combinations turn out to be the constants of nature. For example, the Planck length over the Planck time is exactly the speed of light, right? And that on down the list, all the Planck constants, all the constants of nature are just simple intersections of those Planck constants. Okay, or in this model, simple intersections of the scale boundaries that carve up the fluid of nature, okay, of reality. All right, the next really cool thing, okay, maybe we should pause there if the audience is unaware. There is no other model that I'm aware of, and I've been studying this for quite a long time now, there is no other model that has even proposed a reasonable explanation for any of those constants. This model, just from assuming you have a quantum fluid that is as simple as can be, and then with the second constraint that the size of those different boundaries carved out match the Planck constants, then you automatically get intersections, an expectation of intersections that exactly match all of the constants in nature that determine how all the physical actions in our universe behave. That's a fantastically big, huge, right?
Yeah,
and it gets them to every significant digit. I mean, some of these things we know out to 14 significant digits. It matches them perfectly, right? It's phenomenal. But it goes much further. If we then try to ask, what happens when waves move through this, besides the intersections that those waves have to cause in these boundaries, what happens if we tried to get a stability wave And you think, well, what is a stability wave? Instead of a wave that just spreads out, like you drop a rock in a pond and it spreads out over time, or it dissipates. Think of a wave like a vortex that's balancing itself. Okay, now most vortices that we've seen don't last for very long, but maybe you've seen one last for a couple of minutes, okay, and you can see it can be a really stable thing. Well, what determines whether or not it's stable is how viscous the fluid is, right? If you have a non-viscous fluid, once you form a vortex, once you have waves come together just right to make one, it stays forever, okay?
Yeah.
Now, you could come disrupt it with something else, but if you didn't disrupt it, it would stay forever, right? Okay,
Yeah.
so what happens if we try to characterize under the simplest geometric constraints you need to get a vortex to form, which means it has to twist around and twist around. But by the way, this one is a Mobius vortex specifically. As it twists around, when it comes back around the circle the first time, it's now backwards orientation. And it has to go all the way back around the circle again to end up back where it was. Think of going around the path of a torus donut, okay? And so when you start out on the outside of the donut, and you go around, and when you come back around, now you're on the inside of the donut. And now you go around one more time, and now you're back on the outside. So that's what a basic spinner is. It's something that has to be spun 720 degrees to come back to the way it started, like an electron.
Yeah, exactly.
Okay. You chime in here. Let me see how we're doing.
That's a perfect, there was a very good explanation, and I was kind of like, I read your paper, the recent paper that you uploaded on the Facebook and on LinkedIn. I was also reviewing that, and now I'm starting to understand the whole big picture of the superfluid.
Okay, good. So it's tracking so far? All right, good. So when I wrote down, since you read the paper, you've seen this already, but when I wrote down the just simple symmetry constraints in order to have that condition of vorticity, then it gives us a number, right? It's the equation is just 1 over, I'll call it x as my variable I'm trying to explain, okay? 1 over x plus x cubed over 2 pi. That means you have 3 things being added together, but their association is clear from that relationship, how they vary, okay? And then set those 3 summed together equal to the amount of twist you need to form, 2-dimensional twist, really, you need to form in order to make a vortex. And you can code that just by e to the negative pi over 2, all to the negative pi over 2, which is, by the way, is also I to the I to the negative pi over 2, and then minus the hole, whatever hole you make in the vortex. So that's going to be your minimum scale. So I put MP that, but MP actually depends on what scale you're measuring on. If you were down on the Planck scale, if you zoomed all the way on the fluid down to the scale of the individual spheres, then MP would equal 1. So that equation, the 3 things added together equals I to the I negative pi over 2 minus 1 is one limit, and the other limit is put into Planck mass value for that instead of 1, and then you get the limit at R scale. All right, well, it turns out that the number that gets popped out from that relationship is the square root of the fine structure constant, exactly to every significant digit, which, by the way, also has not been explained. There's been somebody who tried to force an explanation recently, a very smart person, and maybe it was an explanation that didn't make sense to me, but in general, I hear a lot of other physicists say it didn't really hit the mark for them too, so maybe it wasn't just me. But this one is a simple explanation. This is a vortex. The conditions of vorticity pop out this relationship, just like the condition of a circle pops out pi. If you have pi, you're talking about a circle. It's a relationship of a circle. The fine structure constant is the number that tells you, hey, you're dealing with a simple vortex, okay? So, and for those who also don't know, the fine structure constant is the magic number of physics. It's one of the things that's been holding us back for the last 50 years in progress. And Feynman's one that called it a magic number, right? And Dirac said, we're not going to make any progress in physics until we can figure this number out. This one's a really big deal. And for it to come from a geometry, a simple geometric description, to me makes it even a bigger deal, because now we can have more confidence that we know what we're saying, right?
Exactly.
Okay.
So further, if you wanted to continue on that basis.
Yeah, okay. All right, so from there, so far from the simple model of just assuming that the structure of a substrate of reality is a fluid, but not just any fluid, it's a quantum fluid, and therefore has 5 scale boundaries, and we gave them the exact numbers for what those boundaries are. We got all the constants of nature for free, right, without any tweaking. which
Yeah.
is phenomenal. And now from the vorticity equation in that fluid, the simple vortex equation in that fluid, we generate the fine structure constant for free. So far we have a really simple picture that gives us 30 things we couldn't explain before in physics so far, okay?
Yeah, exactly.
Then it turns out that all the mass particles, let me give a pause here and give a side note for people who don't know. So we have fundamental particles in matter that we're trying to explain. So far, quantum mechanics explains, depends on how comfortable you are with it, but it explains the properties of spin and charge and color and isospin and stuff like that that belong to these properties, okay? By explains, I mean it patterns them together, the properties. What the properties are, it doesn't give us much of a visceral sense. Some people have more of a visceral sense than others, but we don't know if they're right. Okay, that's a situation we're in. But it kicks out the predictions just fine, except for when you ask it about the masses of the particles. It says nothing about the masses. Quantum mechanics has no idea. It hasn't even made a guess at what the masses are, okay? It doesn't have a way to. So it's clearly missing something there, right? I mean, I'm not making anything up here. This is, everybody in quantum mechanics would agree, yes, we want that, but they don't know how to get it. Well, it turns out that we got a simple pattern from this projection, assuming we get a vortex, assuming we form that vortex that makes the electron, which is the fine structure constant one, right? What happens to all the other intersections that are now being formed, right? Remember, the fluid has 5 boundary intersections always in it. So if you twist those together, you're going to have different kinds of basically different echoes of the intersection on top of each other. And if you just write down the structure of those echoes, it gives you the masses of all the particles patterned exactly together.
Yeah.
So that I don't even know where else to go from there, honestly, because
Okay. So
that was beyond where I was aiming.
so till now we have you're getting from the bottom down approach, just like the Einstein did for the general relativity, that you mathematically define the model, and then on that basis you find that, that's an explanation, that's another explanation. So what I wanted to ask that what will be the prediction of your superfluid quantum fluid theory? What would it would predict in the real life? Like quantum mechanics predicted decoherence and stuff like that. What would QFT would?
Well, it kind of really just does a really good job at explaining all the things that we currently need to explain. And so you can count them as predictions, but since we knew about them ahead of time, you can call them post-predictions if you wanted, right? But what it does is it gives us a richer, exact notion of what's going on the inside, how the parts are all twisting about and so on inside of spinners. And knowing that means that we can refine how we're trying to do fusion, for example, right? So we can get different kind of energy sources. If we can get over the Coulomb barrier by figuring out how to pulse these things just right in order to get past the barrier that's usually there, or use the barrier to our advantage, right? Then we can get a lot further, presumably. I don't know, with every big insight in science, it's been rare for someone to have a real good, clear idea of where it was going to take us, right? Usually it was just like, wow, we had no idea. And then the world took off from there, right? So I can't say I know where it's all going to lead, but the goal for me has been to try to understand why we have the structure we have. And I'm never going to get to a point where I'm going to say for sure we know, right? Because I think we should always be trying to know better than we know. But I've been wrestling in a world for 20 years now in physics where it seems that no one's even trying to understand the masses anymore. People gave up, literally gave up. But you think about this, the smartest people in the world have tried to do this in the past, right? I mean, Einstein tried, Heisenberg tried, all these people tried to make sense of these, why these particles have the masses they have and so on. But back then they knew of less, right? And if you go back farther in time, we didn't even know about other particles. So since people have given up, since it's attitude in physics, not everyone, there are some bold people still trying, but the system has really minimized how many people are keeping on to that courage, right? But since most people have given up, think what's happened. Technology is taken off like crazy. You have computer programs now that can ask questions 10,000 ways faster than you could in the past, right? Since no one's trying to find the pattern, no one found the pattern. And I don't know if I was just the first person since we had computers to try. I know that's probably arrogant to say, but it wasn't hard to find. As soon as you have a model for how it should be behaving, it was really easy to see that it did behave that way. So I don't know exactly what to say there, but I feel like this is a big sign that the way we've cultured science these days around the world, right, and not any specific country, the culture of science has become too oppressive to generation of new ideas. It's supposed to be the champion of generating ideas and then finding out which ones are wrong. Because if you generate 1,000 ideas, you might find one that's really interesting and right in a new way. Or if they're all wrong, you're still learning about new things when you find out why they're wrong, right? We don't do that, and we really need to get back to doing that. We need to redesign the system so that people get rewarded, like praised for checking something crazy, coming up with a new hypothesis, and people think, wow, that's really amazing. You even thought of that possibility. Too bad it's wrong, right? But for people to connect to, oh, that's an idea I had never imagined, should be the quest we're after, not just which things line up with reality, but which things can we imagine? This should be the goal, right?
Yeah, exactly. Like and in the startup world, like the tech world, people like to have many like billions of ideas, and like only 1% of them survive. And if we have the 1 billion
Yeah.
like ideas in the science, like that 1% that survive would actually change the course of our future. Yeah. So
Yeah. Yeah.
there's just like a tricky, some modified form of last question, and that what would be the possible methods that you like? Already there has been explanation for the constants of nature and the fine structure constant, but what would be the other sort of possible methods to test the QST? For example, the Higgs bosons have been tested through the LHC, and we are recently in LHC, we are trying to find out that to basically prove the symmetry theory that like by studying either the proton decay and things like that. What do you think that what would be like? All right, this would be the definite test. It would be
What would be the what?
that would be
The
the
definite test of
yeah,
determined?
definite test.
Oh. Well, here's the definite test always for a science theory, right? If a theory predicts a certain structure, pattern, or behavior, and that behavior doesn't happen, then the theory is wrong. However, you do have this option for a theory can predict many things, right? But not be turned towards one of them. So then it becomes more complex than that. But here's the goal going backwards. We need a theory that can tell us how to generate all the masses of all the particles and all their charges and all their spins and so on, right? We need a theory that tells us why all those things are related to each other. And we need a theory that can tell us why the constants in nature are what they are, right? We need a theory. If it's not this one, it needs to be a story. And that's what we're really after. Every true scientist would agree. We're looking for a story there. We're looking for a solution. We'll never know if our solution's right, but we certainly know that if we find a solution that gives us those answers, compared to solutions that don't give us those answers, we're definitely more in the direction of right, right? I mean, that's the measure for a scientific theory. If you come up with one that gives you more answer than other ones do, well, then you're going to lean towards the one that gives you more answers. And this one gives us now all the constants of nature over every other theory, and it also gives us all the particles of matter. And I should say, it's not really a theory that's in contradiction with the best theories out there, like quantum field theory. It just refines what we're saying in quantum field theory. So I don't know if you know much about quantum field theory, but quantum field theory just assumes that there's fields, and it's kind of vague about defining fields. It tries to say that they're defined geometrically, but answering the question about what does it mean that they're physically there is kind of seems vague to me about how they approach it. But there's obviously there has to be some real physical fields, but for them it's plural, right? They have many fields. There's a field for every particle, right? There's a Higgs field, and each particle is a bump in the field or its own original field. So you have fields and then bumps in the fields. Or the simple way you might want to say it is that you have the four forces and fields for each, and then you have different particle bumps, particle distortions that stabilize in those fields. So then you have to ask, why do those fields exist on top of each other to begin with, right? I'm not saying it's wrong. In fact, what I'm doing is really clarifying what we mean by those fields. In a quantum fluid, those fields just are the intersection boundaries of the structure of the fluid itself. which makes it less mystifying, not more mystifying. It makes it very clear. There's no field now. There's no magical thing that's, you think magnetic field is something that's invisible but still does stuff, right? Now it's something that's no longer invisible in your mind. You know what's doing it. You know why. And so it's like seeing levitation of sound waves and some sort of thing floating above the sound waves. When you see it at first, you're like, wow, that looks magic. But then when you figure out what's happening with the sound waves, you're like, oh, okay, it's not magic. It just looks like it at first, but it's clear. This is doing basically the same thing. It's taking the idea of quantum field theory, but they're saying, hey, those fields aren't magical things we just throw into existence. They are consequences of they are the boundaries which are the consequences of fluid quantization. Just because there is a quantum fluid, they exist. And the vortices that form in those between those boundaries cause all the structure in all the particles of matter. That's pretty simple. In fact, it made their whole thing even simpler. Still, it would be exciting if I had that story to tell, but I couldn't get the numbers to work out, right? But the fact that the numbers work out is more important, because maybe you'll come up with a story that's slightly different, but still compatible with the numbers. What we really should harp on is that, hey, for the first time ever, I don't think anyone's ever come up with a simple explanation for the mass of the electron. Just the electron, right? Let alone something that stamps all of them at the same time, accurate to every significant digit. That alone is phenomenal, because we didn't have a pattern before. Even if it ends up being wrong, which at this point I don't even know how it could be wrong, but if it did somehow, maybe there's 10 more particles we find in the future and this one doesn't project them, and it's only a partial pattern. It's still a pattern that explains all the stuff we know today, right? And that's, I don't know, to me that's it's hard to calm down on it, really.
Actually, like being a science physics enthusiast, there are like a couple of questions in my mind, and mostly are like related to the cosmic web and like EA theory and stuff like that. So before going into that part, I would like to ask you a simple like about your recent book, The Perfect Universe, manual to the God, the guide to the God. So
I got it right here.
yeah, exactly, that one. Yeah. So
I'm really happy with this one. Okay, so in prison, I had a lot of time to do a lot of reading, a lot of thinking, and I read every physics book I could get my hands on. I taught astronomy and basic science and art and everything I could to be doing education, but also it gave me access to people who were appreciating these conversations and people who got out before me, and they would, as a favor, usually mail in a book. So I would get eventually all the physics books that were, they were commonly out at the time, not all the ones from the libraries, but the ones coming out in magazines being advertised. And I would read them and try to make sense of them, and sometimes feel like the dumbest person in the world, like, why didn't I already understand that? Or why can't I get this? But I would keep track of all the big questions, right? I'd keep track of what people say the answers are and whether or not it made sense to me. And eventually I started finding the categories of things that, yeah, we really do have a handle on this stuff. And then there's categories of stuff that it feels like we have a handle, but people disagree. Like they all say it means this confidently, and then someone else says something different confidently. Like it's not exactly clear. And then there's the category of stuff where everybody boldly agrees we have no idea, right? Once I was able to sort that out, I wrote an entire book called Einstein's Intuition, which is a lot longer than this one, but it was basically tracking the entire quest of trying to answer those or ask those questions, finding out what the big questions should be, following Einstein's quest and finding his insights, which are remarkable, by the way. It really does something to your brain to learn or to train it how to think in higher dimensions, in more dimensions at once, for example, right? And that's basically what Einstein did. He found a simple geometry that if we would have had computer graphics back then and make things just dance around in 3D on a 2D screen, it would have been really easy to say. But at the time, he had to think of it as geometric expressions, as relationships, right? Anyway, so I wrote that book called Einstein's Intuition, mostly while I was in prison, finished it up when I got out. And that's been fantastic. But this one, A Perfect Universe, now has been the follow-up. So Einstein's Intuition was trying to build my direction for how I think we should try to answer these questions, my gut and feeling after all that research for what the solution which direction we might find the solution, right? And it was under the guess that there was going to be a fundamental fluid. It was following pilot wave theory. That was my favorite direction because it had more fluid dynamic essence to it. It had more clarity, but more importantly, it's defined explicitly. Pilot wave theory isn't an interpretation of quantum mechanics that's vague. That's the best thing you can say about it. That's the best thing you can say about any theory. Pilot wave theory is specific, and it gets the predictions right. So you can't say that about the Copenhagen interpretation. So nobody should ever favor it. It's not even specific. It's vague. So why would you try to rest your laurels on it, right? The pilot wave theory is, or Bohm mechanics, or de Broglie-Bohm, there's all these names for it, okay? It's also advanced further since then, and some of the people who've written the best papers on it are people that are, I like to think of them as friends, but really they're mentors. They're really amazing guys. Yeah, that I think we should keep in mind that pilot wave theory is explaining quantum mechanics, right? Quantum field theory tries to take that sort of explanation really more in the Dirac form. It used Dirac theory instead, but it uses basically wave mechanics, right, to put together the long equation for how everything works. But there's like 50 variables we need to put in there in order to make it work, right? Yeah. So now all we're adding in this short book is the description of the fluid, like we did in this talk here, specifically defining the characteristics of a quantum fluid, right, and following the consequences from that pattern. And then finding that we get all the constants of nature and the particles of matter, and something I'm really excited about, end up deriving the vortex equation. That was a shock, because to me, we now have in fundamental math, we have 1 as a fundamental unit. We have pi as a fundamental unit relating to circles. We have je as a fundamental unit relating to the vortices, right? And we have E. And E is a fundamental unit that binds 5 things perpendicular together at the same time, which might sound like a weird thing. I don't know if you've ever heard it said that way before. E is a phenomenal number. It's the number in which has a power association such that its own derivative is equal to itself, right? Think of that. That's the only number that can say that. So it's, well, except for 1, right? So E is phenomenal, but here's a really awesome thing that you wouldn't have expected. If you take the 5 numbers that characterize the boundaries in the fluid, okay, and you take the union of those numbers. So let me explain what that means mathematically. You take the sum of all their powers, but take absolute value of the powers. So each one, say, let me look at what they are. But the Planck length is, the Planck time is 5.391247 times 10 to the negative 44 seconds. Okay, so first thing to notice is there's a unit of seconds, and it's arbitrary, right? Because humans made it up. It's not a natural unit. And there's a number, but the number is in base 10, and it has 2 parts. It has digits, and it has a power of base 10, okay? So it's got 3 things important here. 1 is an arbitrary unit, a base that we're in, but the other 2 are a power, which has to be a whole number, and a string of digits, which is not a whole number in any of these cases, okay? Well, if you sum up all the powers in all 5 numbers and divide that by multiplying all the digits of those 5 numbers, you end up equaling E.
It was a very difficult. I have to do this little math over there. Like after this interview, I will do that.
Yeah, it's also in the book. If you look through it before, it's mentioned in there. So yeah, basically, when you blend those 5 boundaries together, you get a blend, an interaction blend of 5 things. You have a power to product association equal to E, which is, to me, phenomenal. Now we have 1, we have pi, we have E, we have je, and we have what else? Yeah, that's good. Yeah.
All right. So, like, there's have been questions around in the comment sections. So,
yeah, cool.
Most of them they're like enthusiasts, like physics persons like us, like stuff like that. So the question is that why the time flows only in one direction?
Because think of a sphere that's bouncing. Okay. Now run it backwards. Same thing, right? So time is the cutoff in the fluid for the cutoff that you can resolve an action in the fluid. So if a fluid is made up of pieces, that means if you're having a wave that's a front in the pieces, is made up of a collection of them, right? As that wave front is moving, to interact, it has to interact with the things it runs into. But since they have this frequency, the fastest you can do is one interaction per one of these guys, right? Which is actually why it's the Planck length of the Planck time is the speed of light. That's the fastest speed you can do. You can go slower. You can be sitting still and interact with one thing many, 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 many times before you move on to the next one, right? But the fastest you can move is hitting this one, and then this one hits that one, and this one hits. So that's why it's the speed limit, because there's a limit to size and time. So time moves forward only because time actually is a symmetric operator, but it always moves forward because it's increasing in entropy. It's actually a really complicated question. I don't know exactly what level the person who asked it on. It's a really important question.
Undergrad. Actually, that same question often comes to my mind, that why does the time even move? Like, why does it even...
Say it again?
Why does the time even have to move? Like, why?
Why does time even have to move? Well, if it didn't move, would you just then be frozen waiting for the next moment? And then when the next moment happened, you would have the next thought? I mean, there's no way to distinguish whether it did or didn't, right? So it's more like, why are we able to recognize patterns in existence? Time is necessary for that recognition. So it is a fundamental question, why is there time? But if we start from the assumption that the fabric of reality is a quantum fluid. Now mind you, there's lots of questions as to why we're starting there, right? Why? Where did that fluid come from? What caused the fluid to exist? Those are all important questions. But if you grant that there is a fabric that's a quantum fluid, it's fundamental here, that we're all in that fluid, right? Then time has constraints already with it. It has a minimum, and it has cutoffs, but it also has symmetry. So these waves symmetrically interact, and that symmetry makes it so it's always trying to scatter towards higher entropy, okay? So all the actions the substrate supports are time symmetric. They can go backwards or forwards, they can do all of them, which makes them symmetric in time, okay? But the asymmetric things that we measure in reality aren't symmetric in time. So the things that we exist, let me back up. The 5 scales that we talked about, the fluid being, that carves up the fluid, right? They're all extremely scale asymmetric. They're not close to each other. They're many powers different. One's many bigger than the last one. The next one's many powers bigger than the next one, okay? So they're very separated in a sense, which makes them extremely asymmetric. But so if that asymmetry didn't exist, then time wouldn't flow at all. Or it depends on what you're meaning by time in your head when you say that sentence. If that symmetry didn't exist, there wouldn't be anything to recognize for which you could point to something different later, right? So there would be no way to reference time.
All right. So there's another question that do you think the cosmic inflation is explainable by the deterministic model?
By deterministic model?
Yeah.
Yeah, I think everybody who's trying to explain it is trying to explain it by a deterministic model. And mostly because it's a large effect, so all you need to do is have a pressure term, or you need to have something that's causing it, right? But once you've listed the thing that's causing it, it's deterministic. Usually the divide between determinism and stochastic or indeterminate representations of something like quantum mechanics isn't a divide of, is it actually deterministic? It's a divide of, can you identify the relevant variables that are causing this phenomenon? And if not, but you can identify the collection of them easily, then your description of the actions will now be statistical, right? They'll generally be right, but they'll statistically be right. But if you identified all the internal variables that are making the system do what it's doing, then you have an exact description, you have a deterministic description. So I think the goal is almost always, there's some people now that maybe believe that it can't be a deterministic one. I think they don't even know about Bowie mechanics. But I think some people are trying to push that it's even possible, but it is the scientific goal. You're trying to determine what's going on, which means you have to model deterministically what's happening, right? So that is the actual primary goal of science, is to determine what's going on, or to determine whether or not your modeling of the world accurately captures it and therefore counts as a model that we should believe in. Ooh,
Right.
there's a great place for us to talk about. Let's talk there. Let's have everybody think for a minute about how we don't actually perceive the world around us, right? You're not seeing, there's not a projection of stuff out there that's coming into your eyes as is, and you're just seeing what's true. What's happening is photons and other things are bombarding your body. But let's just talk about light. So photons from things around you are coming into your eye and then exciting your eye and sending a signal to your brain, and some process in your brain is figuring out what to do with those photons. And then your brain tries to figure out, because it's trying to predict what's going to happen in the next few seconds, the next few minutes, next few hours. It's trying to help you predict your way through the world. So it has to build a model for what those photons meant. And it trial and error at first until it figures out when you're younger, right? But think about this. If your brain picked something wrong, if it always has been lying to you, or if you've made up an assumption in your head about what the world is, and every time you see that thing, you make the same assumption, then you're actually seeing the world that you believe in, even if it's not there, right?
Yeah.
So that's the human condition. We're stuck in this place where we're trying to measure reality and get a better understanding of what reality is. But we have to first always remain aware that what we are seeing is what we're projecting from our expectations, from our beliefs about what reality is. And as that changes, as we figure out different ways to assume that reality interacts or what it is, then what we see in the world changes with it. It's phenomenal. It's like it literally can see different things or pick up different behaviors, or it changes everything because we project it differently.
Yeah. Okay. So on that note of determinism, there's another question of Bell in theorems of inequality. So what are your notes upon that?
Can you ask that again? I cut out a lot.
Yeah. All right. So on the basis of the determinism, and there's a question about the theorem of the Bell's theorems of inequality. So what are your notes upon that?
About the Bell inequality?
Yeah, exactly.
All right, so where do we want to start with this? So Bell's realization, let me assume that the people listening have never really gone into this before. So Bell noticed that some assumption that we really wanted to believe about the world has to be wrong, okay? Now, it's technically one or the other, but we wanted them both, so let's go through them a little bit. We want to believe that the world is realist, okay? That is, that what we're describing over time as scientists about the exterior world is actually matching better and better with what's actually going on. Maybe we're still pretty far off, but we're getting better over time. So we want to believe that that's true. And that believing that means you're a realist, okay? And we also want to believe that these actions, the universe itself is always local. Local, LCAL, meaning as COL, sorry, meaning that if I do something here, that effect can't travel instantaneously and affect anywhere else. It has to travel through the medium that separates the two objects in order to affect the other object, right? So, and there's a maximum speed of light in order to get there. Violating local realism means that you get effects where one thing can affect another thing before the light could have gotten there. Okay, so Bell's inequality basically proves, abstracting everything else away, that it is a condition, given quantum mechanics is true, which its results are true, right? So given that the quantum mechanics results are right, then we cannot say that the universe is local realist. It conforms to local realism. So you can give up both. It's not realist at all. It doesn't represent what we're actually thinking, which seems kind of absurd and crazy to me. Or you can give up the locality and say that, oh, it doesn't conform to the rules of locality everywhere. Okay, that's great. That just tells us that there's something different than we thought, but it doesn't tell us what it is, right? It doesn't tell us how does it conform. And so here's a way that it conforms differently. Spinors, again, are a very good example. In a spinor, the object behaves in a way that's very, very different from normal objects, right? Look at this object here. If I spin it around 180 degrees, 360 degrees, and now it's back to where it was, right? It's back the same. But if I did that to a spinor, the spinor would go around once and it would be somehow backwards it would have to go around again a second time to be normal. And we explained that earlier what it was. Imagine a vortex going around a torus loop, right? So if you go around, if you start on the outside of the donut, start out here, as you go around, you come to the inside, and you go around a second time, come back to the outside. So in a sense, you're still going around once, but end up reversed, exactly -1 from before, right? And you have to go around twice to become back normal. So there's an example of some structure happening that doesn't conform to locality. It twists the world up in a way that shouldn't have happened if there was locality. So it's not a bad thing that Bell came up with this or figured it out. It's really that he found an abstract way of arguing this so that we couldn't ignore it anymore. You couldn't just say, oh, it's just that one experiment. He did it abstractly, so you can't just argue it away with one experiment. It is a rule, right? So then we started looking. I think the big problem was that people were very uncomfortable with things not being local, because all the math we do with the XYZ coordinate plane, all that stuff, it's all assuming locality from the beginning. It assumes it so much, we don't even mention it ever. It's so fundamentally assumed, they don't even tell you on class 1. It's just kind of, you figure this stuff out. Kind of, it's so obviously assumed, right? People are used to assuming locality holds so much that when they hear someone propose that it doesn't, they want to try to reject it. But Bell made that impossible. You can't say the locality holds everywhere. You can say it approximately holds most places, right? At least on all large scales and so on. But on the small scales, it does not hold always. It can hold and it cannot hold. But interestingly, if we go further, we can say, what does it do? It only does specific things that have mirror symmetries, that have doublings, right? So like the double cover of the spinner. So it doesn't do anything else. It's not like when you break locality, you can do anything. Instead, it's when you break locality, you have one other way to act symmetrically, okay? Which is fantastic news. It's a huge clue to figure out what the hell's going on in reality. This, by the way, mirrors perfectly when you're going up the structures of normed algebras. So we start out with the real line, number line, right? Yeah. And we use the real number line to characterize operations we can do on something. Try to keep it as general as possible. You can add, so +2, and I can then -2 to get back to where I was, okay? Very important operation. We want all operations to be interchangeable, meaning I can do it one way and I can come back to where I started. I can undo it. So plus has to, if you have a plus, then you have to have a minus so we can get back. You have to get back the same way also. You have to get back in the inverse way, right? Not just some crazy combination of ways. So if you have an operation, you want to have its opposite operation, and then you want to assign what those operations are doing in your explanation, what they mean, okay? But the real number line's got a big problem. If you go, let's say we extend from 0 all the way out to infinity, right? You get 1, 2, 3, 4, and you keep going. But then let's give negative numbers because we had to have minus numbers in order to do plus, right? To cancel them. So now we can go to negative infinity. But let's say we want to do more than just plus and subtract. Okay, great. We can multiply. All right, so we start somewhere and we multiply by 17. And we get up to some other number. And now if we divide by 17, we come back to where we started. Awesome. So we can't just multiply. We have to have multiplied and dividing together. But what if we want to say, all right, I want to start at 2, and now I want to do a different operation. Let's call it, I want to square it. Oh, now you go up to 4, and say, okay, well, opposite operation, square root it, back to 2. Great. What happens if you started on the negative side of the line? Then what do you do? Now you're fucked, right? You can't do anything. You're screwed. You don't know what to do until you realize that, oh, numbers, the number line, the one-dimensional line we've been imagining doesn't characterize the whole of numbers. Numbers need something else. It turns out not just one. I'm going to introduce one more, but there's really 8 dimensions. So numbers are all 8-dimensional, and they form a closed set, right? They form a closed set in the sense that they're infinite, but a closed self-referential set, meaning all the operations you can do, like adding and subtracting, multiplying, dividing, squaring, or powering, and inverse powering, right? Even on the negative side, works on the octonian structure. Or in this case, if we just move up to there, it works on putting the complex plane. So now we can rotate things in the complex plane and do square root of -1 and have it mean something, right? It means that the operation actually had 2 parts to it, and there's a second dimension. That second part is perpendicular to the part you're interacting with, but it's still there. It still has an effect, right? That's really all that's really meaning. But okay, I think I got lost of what I was trying to answer anymore, but
It was locality theorem about Bell's locality theorem. I should like review the questions if there are any other. Wait, all right, so like I think we should move on to there's a generic question like what is the coolest thing about your research? I think we should have like
the coolest thing is getting to a point where you find something. It's like you've put together big puzzles before, like 5,000 piece puzzles, right? It can be if you get into the mood of it where you're really trying to figure out, okay, I want to make my brain trained to put this together fast. So you're trying to pay attention to big general details and put things together. And when it comes together, it's very satisfying. Now, imagine though, instead of the puzzle, we were talking about reality itself as the puzzle, right? And you're trying to find all the basic ingredients. So first you're trying to gather all the puzzle pieces and then figure out how they all fit together so that you can see what the picture is. So you can see what the structure is telling you, what the form of reality is from that. And that's really the goal for finding all these answers, right? Is to get that kind of answer. The most exciting thing for me is that we've actually made some progress. Even if we end up being overridden in the future and someone comes up with even better, right? And sometimes this is the first time anyone can ever say that they had a pattern that stamps all the mass particles, all their masses simultaneously, beautifully, right? It's such a beautiful pattern. Like, let me show it. This is my version that I'm drawing all over the place, but it's this simple. You can see how everything repeats. There's a power tower of 2 association. There's a phase association on the top 3, and everything else just has the same structure. So these are simple boundary intersections, rules of boundary intersections expressed on each level out from the center, the core of the vortex, right? That structure is just literally a structure of a factorization of these boundary conditions and phase options for the boundary conditions. So the phase on top of factorization give you the matter structure, which I find so convincingly beautiful, so beautiful it's convincing, right? That's basically, so for me, the most exciting part is the aha, I understand something more, I understand something better. And then it becomes a cascade of new things I need to learn, right? Oh, there's so many different fields in math. There's no way to be up on all of them. It's just really difficult.
Right, there's another question like, what are the major challenges you face during your research? Major challenges.
The major challenge is a few. It's very difficult to be somebody who's a paid researcher working on fundamental questions in physics these days. It shouldn't be the case. It should be that we are encouraging artists and scientists of all kinds to foster their own creative ideas instead of wasting all day going to work in jobs that just waste their talents. We should restructure the world so that we are valuing people for their ideas and trying to get them to generate those ideas instead of squashing those ideas and wasting them all day. But on top of that, me personally, the challenge is, well, personally, my one big challenge is I've been to prison, right? In the world, when you come out into prison, you get many different reactions from that. But in the academic circles, the first reaction is going to be hesitation, a little bit of skepticalness, right? Compounding that, far, far worse than that aspect, is the fact that I'm working on fundamental physics, which means if I were to ever say to somebody, hey, I have a solution to something that hasn't been answered since Einstein tried, everyone's going to respond with, I don't have time to listen to this. So that's the big problem. So that's why I write books, to try to explain logic step by step, right? To show, hey, this is not a bamboozling. This isn't someone trying to convince you to believe their way. This isn't a religious point of view. This isn't somebody trying to scam you. This is somebody pointing out that if we make simpler assumptions than we're making now, we generate things we can't generate now. So that's a reason to believe that it might be like that or closer to that than what we're saying otherwise. And I think we should spend some time actually trying to make ourselves comfortable with this model, because as we do, we have different relationships formed. We form different relationships with these mysteries, with these matter particles, with the constants of nature, with the structures, how they form on top of that. We have a different impression of who we are as composites of all these kinds of particles, right? So in as much as all that structure is coded into these intersection options, excuse me, it's extremely exciting. So, yeah.
Right.
Talking so much makes me cough. Sorry.
You can take like a break. I was worrying about your health. Like there's a COVID-19 pandemic, and that's really matters a lot. So uh, I would like to wind up the whole thing, and like, what will be your final thoughts for the aspiring theoretical physics, the undergrads who would like to be a theoretical physics to discover the next big leap, and things like. What would be the advice for such things? Like,
If you want to go into theoretical physics, or let's word that even better. If you want to devote part of your life to trying to uncover more of the secrets of reality than we currently know, then my advice is, one, to learn how to take advantage of the things people have already figured out. That's the first huge step, right? Don't invent it all yourself. Don't try to figure it out yourself. Don't try to invent calculus yourself. Try to first learn the big insights that people have already come up with, but not to memorize the process. Not to memorize the output, right? Like memorizing how to do integrals and derivatives. It's useless to memorize how to do them unless you know how to apply them. What are we saying when we're doing this? And if you can keep track at every step through college, those simple things. I think most people don't enjoy math, which is a shame. I kind of want to go back and start over and get a PhD in math now, because if you introduce the right way to math, they are fundamental mysteries. You don't even need to connect it to physics, to the physical world, right? There's fundamental mysteries in math that are beautiful. Structures in math that make you just wonder, why is that there? Like, it's really fundamental, but you need to get a good relationship with math. And here's the secret. Everybody's intimidated by math. Everybody. Maybe not Edward Witten, right? Maybe not him. Maybe there's 4 people in the world that don't feel intimidated unless they're just crazy. Because the thing is, even if you're really, really, really good at some specific math, there are so many other maths that you don't even know what the symbols mean until you've started, right? It takes a lot of background to catch up to what the conversation is in some very specific mathematical fields. So don't pressure yourself about being uncomfortable with math, about not knowing what it means. Give yourself enough time to be around the equations to figure out what they're trying to represent and ask questions. I think that's the main value, asking questions, and consider yourself owed an answer of sorts. Maybe the world doesn't owe it to you, but you should demand it from yourself. You should demand, I am going to find an answer to this thing. Pick something that you're curious about. It doesn't even need to be physics, right? But pick something that you've seen happen that doesn't make sense to you and you want to know why. And then just take on the quest to figure it out. If you add that personality trait to somebody who's going through the college years, whether or not they always pick something related to physics, if you did one per day, by the time you've gone through 4 years of college, you have asked all the major obvious questions to ask, right? You've now complemented your education with a personal quest along the way, which hopefully reinforced the understanding of your education. And now you're qualified to really start asking some interesting questions. You could have stumbled across them earlier, right? But now that you've seen how everybody else asked the important questions and got insight from the way they asked it, not from the answer, but from the way they asked it, right? Now you can go on and try to make sense of the world and contribute something that the rest of us haven't figured out, and therefore change the way the rest of us see the world.
Okay, thank you very much for such a beautiful note. It was really exciting to have you on the board, and there are a lot of things I learned from there. And I think audience like the critical thinking, that part is very essential. To question everything that you know and you are like mystified of it. That is a very good point. And like finalizing this, I think the interview should be like ended here. Like it's been more than an hour here. It's been sorry, that's I'm like skipping the things up. So at the final thought, 5K seconds. If like if Thad Roberts would be more into like QST, like when you discover the things up more into QST, like I've read your recent paper that's it's like it's still like, math is still working on up, right? So as you further progress, I would like to have you on the 5KS another time. and that will be again very mystiful and a good experience. And for the viewers, I have a link in the description, email of the Terry Roberts. You can contact him for any direct questions to him, or you can actually join our group Papyrus for further discussion about the ideas and the knowledge. So at this point, I think we all are good and good to go. That was a really nice experience. And thank you, Terry Roberts. Best of luck.
Yeah, thank you. All right, bye.
Assalamu alaikum. After all, it's that. Yeah.